Hi everyone, so today we'll be talking about algorithms. Many CS students call algorithms boring or a waste of time, but they're actually very SUGOi and KAWAII. So we'll talk the different flavors of algorithms and demonstrate them in a problem. By the end of this video, you'll be able to show any technical interviewer just how SUGOi and KAWAII algorithms can be. So stick around. Alright, before we dive into any of the details, let's take a look at the algorithmic design process as a whole. The first one is understanding the problem. That means you gotta read it carefully. You're gonna want to ask questions, get some clarifying on there. Then a vital part is understanding what your input's gonna be exactly. Like, what is the algorithm gonna be working with, and what is it gonna be outputting? What are you trying to get as the final result, right? Then after that, we can do a small example by hand to get a good grasp of everything we're dealing with. And we're going to want to identify edge cases, basically little areas where your algorithm can get screwed up in the problem. Then after that, you want to use something that already exists, a technique that's already been around, been established, been proven to be super fast. But if none of those seem to work for your problem, you can get KAWAII with it, and you'll have to design your own and figure it out. So that's all just understanding the problem. After that, we're going to move on to... One sec, let me erase. We're going to move on to deciding computational means. So that's basically talking about, are you going to be sequential in your algorithm? Or are you going to be parallel? Now, most of the time you're going to be sequential, which means you're going to be going down a list of instructions one after the other. Whereas a parallel one, you'll have instructions operating at the same time to give you a faster result. Not everything really works for parallel, so most of the time you'll be doing sequential, and when we analyze the time efficiency, we'll be assuming sequential. But yeah, let's see. Then we'll have to decide on exact or an approximation solution to our problem. Oh, I can't spell. Approximation. There we go. So you're probably going to say, hey John, why the heck would I use an approximation if I can use an exact? Well, buddy, some problems you run into aren't going to have an exact solution. You'll, like a definitive one only kind of thing. You'll have to find an approximation. And a good example of that might be solving a nonlinear equation or something like that. So yeah, we'll have to decide exact or approximation. You're going to go with exact 90% of the time. Then after that, what do we got? We have to decide on a general algorithm design technique. Yeah. So these are general approaches to solving the problem. And this is a part of the designing phase. We'll be talking about some of these in the rest of the slides, or sections, or whatever you want to call it. And yeah, you have a whole list to pick from. You can mix and match them if you need to. And of course, you can get KAWAII with it and make something totally original if you're desperate for a solution. And you get to specify the details of your algorithm using pseudocode. We'll have some examples there. That's not really like English where you're like, hi. It's more like, or even any syntax specifically. That's just like a general for thing, this, like do, while. Like, it's no actual syntax or anything you can actually put on a thing and actually get to compile or nothing. It's just a good guide for understanding what you're going to be doing. And then after that, you're going to want to prove your correctness. You want to show that that it works and gives you a solution. And you usually do that with math, you know. We'll talk about that in the next section as well. And then, of course, after that, we move on to analyzing the algorithm. Now, the most important thing that you're going to be analyzing is the time efficiency, how long your algorithm takes to run. And you're not doing this in like actual time, like milliseconds or anything. You're doing this in like instructions, like the number of instructions it's going through kind of thing. And that's described with like this whole math thing that we'll talk about in the next section as well. So yeah, oh god. So yeah. And then finally you code it. You put it into some language you know or kind of know or say that you know and fake it till you make it and try to make it output stuff and then debug and do all the fun stuff you have to do there. Yeah, that's the general process. Pretty simple, pretty cool. Pretty kawaii and SUGOi, of course. I won't be using this for the problems I show you, just because, it's pretty verbose and detailed, and, it's definitely by the book, and it's good to do. It's good to know about, but I don't know. I'm not going to use it. Alright. Okay, now that we know the problem-solving process that we're not even going to use, let's learn about algorithm efficiency. This little chart here describes it perfectly, to be honest. All the classes of algorithm efficiency are listed here. It's based on the scale of input with the number of operations in our algorithm. So you see input rises and our operations rise, we get our efficiency very exaggerated. But if you notice down here, you'll see that on a very small input that you might see for like a homework problem or just anything tiny, the efficiency of your algorithm won't matter at all. It's basically the same. Or even, what's even crazier, an inefficient algorithm can even actually beat a more efficient one. You can't really see it on the scale, but yeah. Anyway, we can determine the class of efficiency by doing some math. So let me set up a nice example for us. We have, what's it called? A non-recursive example to look at where it's the max elements in an array. So to set this up, we have an input of an array. And we have an output of max value in it. So with that in mind, we can set it up as max val initialized to the first element in our array. And then we can do for I equal to 1 to n minus 1 do if ai is greater than max val, then we want to set max val to ai. Yeah, you can see it. Anyway, well, after all that's done, we'll return max val. Alright, so now we can see this is our loop, and we want to look inside the loop for a basic operation that'll run every time with the loop. And we can see this comparison fits that. So this will be our basic operation, and it's only one, and it's only running one time. So we can set up a nice summation formula right here with n minus 1 and I equal to 1. And this translates to 1 plus 1 plus 1 plus 1 dot 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 n minus 1 times, which is just going to be equal to n minus 1. Now, since that's going to be our thing, we know that the dominant factor in here that will scale with input the most is going to be n. So that would make this O of n. And that gave us our efficiency for this algorithm, which we can see right here is pretty fair. It's also called linear if you're a nerd about words. It's a linear efficiency. Come on, give me the eraser. But life can't be that simple. We have to also do recursive version of this. And that can be modeled by this problem here, where we compute n factorial. So to compute our n factorial, our input will be a positive integer n, and our output should be n factorial if we do this right. So then we can write our thing, our algorithm, as if n equals 0, we'll return 1. And else we'll return f of n minus 1 times n. Okay. So this is basically the idea of recursion, right? We'll be using an input of n, throwing it into our function, and if the function isn't 0, we'll be calling it again, but decremented. So this will run until we reach the base case and return 1, and then it'll work its way up the stack into our final answer. That's how recursion works. That's the word. So with that in mind, we can try, let's see, we know this is going to be the recursive call. That'll be important, and we know this is our base case, what it's basically recurring down to. Now we can model this. Now the operation that'll be worth measuring to figure out this, our efficiency, will be the number of multiplications, because that's the operation we're doing on each recursive call, all the way down, right? So we can model that as a recursive call as f of n is equal to f of n minus 1 times n. So we have our recursive call, and if we want to measure the number of multiplications, since that's our operation, we can model it as m of n minus 1 plus 1, because we have this adding to it each time, and we have this for the function calls that are running through the whole thing. So this becomes our recurrence relation. It's a big word, or big 2 words. So you want to find your recurrence relation when you're trying to solve the efficiency of a recursive algorithm. So now that we have that, we can model it to try to find a pattern, or trace it, I should say. Let's get some more room here. There it is. Come on. Oh, come on. Come on. First time. Yeah, it is. Let's see. Yeah, good enough. Alright. Oh my. I'm gonna cry. Oh, we're good. Alright. So if our thing is m of n minus 1 plus 1, our recurrence relation, we can trace it. What are you doing? There we go. With each iteration of our thing, of our recurrence relation, and we'll see that it becomes n minus 1 minus 1 plus 1 plus 1, right? And then do it again, we'll see m of n minus 1 minus 1 minus 1 on the next iteration of our thing. So this is basically, well, this one is m of n minus 2 plus 2, and this one is m of n minus 3 plus 3. So we can see the pattern emerging as a way to form a general form of our recurrence relation as n scales. And we can describe that as, with each iteration, we can replace these constants with I instead of these numbers. because you see, with each time it runs, we're just replacing it with I, basically, because it's summing to that I. So yep, we get that as the general form. And with that as the general form, we can then jump to an assumption of n iterations to make n minus n plus n. So if we're going to have n number of i's, we can just substitute it there. And with that in mind, that doesn't matter, but this does, and it becomes big O of n. That's our dominant factor in that one, and it leads to us knowing our algorithm's efficiency for recursion. So yeah, that's how you want to do any algorithm analysis. Is you want to use math to figure out what your class is of your time efficiency. Alright, so the next algorithm design thing we'll be talking about is called the brute force algorithm. It is basically KAWAII is the best word to describe it. It's considered straightforward and not like the novel approach. It's not clever, it's not efficient, but it's there for you when you need it. Some problems only have a brute force solution. Those are like NP hard problems or something, some term. And this design works fine for small input sizes, but like I was talking before. But it is very bad for large input sizes, and yeah. But it's simple and direct, so it's got its it's got its plus sides for sure. So an example I like is called the knapsack problem. And this is a real computer science thing. It's wherein you're given n number of Hatsune Miku figures, and they each have an assigned weight, and they each have an assigned value to them. Like maybe you have a special edition one, I don't know. And then you have a knapsack weight capacity. So you have a limit on how many Hatsune figures you can grab with you. So we'll have a nice little chart here for the number of items, or not items, excuse me, figures, number of figures, their assigned weight, and their value. So for this example, we'll do 2, 5, 10, 5, and then we'll do 20, 30, 50, and 10. Yeah, these figures are cheap. We got them in the clearance bin. And yeah. So with all that in mind, we'll want to generate each possible subset and their associated value while maintaining the weight capacity limit. So this one's tricky to generate all those things, but I like a nice little trick. Wherein if we're using 4 different things, so 1, 2, 3, 4, we can generate their entire subsets by doing a nice little binary trick. Wherein, how did it go? I think it's 4, I think it's 8, right? 8, 4, 2, no, it's, wait, no, yeah, it is 8. 1, 1, 1, 1. And then you alternate it. Oh wait, no, I was wrong. It is, okay. We'll need a bigger scale. Whoops, we got way too many possibilities for these figures. We gotta stop buying so many figures. It's bad for our math. Mother, God, why are you being hard? Oh my mother of God. Alright, so for the figures, it's going to be a little tricky to write, but we'll get it. Figure, weight, value. Oh wait, no. We already did that trick. Okay, so to generate all the possible subsets, we know that for any n element set we're going to have 2 to the n subsets. So we can generate that by making a nice little graph of the charts. So we'll have 16 possibilities here. I'm using a little trick I learned in my binary class for, I don't have enough room. Alright, let's try that again. So with every possible subset modeled, we know, oh shoot, I forgot the values. What were the values? They were, alright, so now just to make it clear, with all that in mind, we have all that modeled, now we can figure out the weights and values of each subset. So weight 0, V0. Okay, so the weight of 4, 10, value of 4, 5. Weight 10, V5. I never looked at our capacity. And it doesn't matter, I can just make it up. Let's have a capacity, let's see, 5, 10, 5, 2. Let's have a capacity of 15, I don't know. You can carry 15 weight for your Hatsune Miku. So then 3, the weight. So for just 3, it'll be 50 value, 10 weight. So 10 value is, what was it, 50. My brain's turning off. So then the weight of 3 and 4 is 15. Ooh, that's good. And the value is 60. That's a contender. And 1. Let's see if we just have 2, it's going to be just 30. Oh, I'm sagging down. And the weight is equal to 10. No, 5. Whoops. Ooh, this is turning into a real hot mess. Alright. But you just had to bring Hatsune Miku, didn't ya? 30 and... Is that 10? Yeah. So value 40. Weight of 2 and 4 is 10. Then for 2 and 3 is 80. And weight is 15. Okay, that's a good contender. So for the 3, it's going to be 80, 90. And the weight is going to be 20. No can do. And then for just 1, it'll be 20. And the weight will be 2. That's bad. And then that one will be value 30 with a weight of 7. And that subset will be a value of, was it 1 and 3? So 70. And a weight of 12. And that one will be for the last 2, 1, 3, 4. What is that, 80? I'm dumb. Then 17. Alright, so 80 and 17. So that one's bad. And for the first 2, it'll be 50 with a weight of 7. And for the first 2 plus the last, what is that, 50, 60 with a weight of 12. Yep. And then that one, first 3 will be a value of 100. Look at that. With a weight of 17. Damn it. And then for our last one, well, we know it won't work, but it's 17, 22 for the weight, and the value is 60, 90, 110. That's what I got. Did I do that? 50. Yep. Alright, that's bad. Alright, so this means our best value after searching everyone, I believe it's this one, but now my bad handwriting's catching up to me. I'm pretty sure that's it. So our final answer would be items, we can bring item 2 and item 3, or figure 2 and figure 3, with the value of the 2 and the 3. So yeah, that's the knapsack problem. You need to go through every possible subset in excruciating detail and then find it. This was a very simple example. You probably figured out it was going to be that one very quickly, but it won't always be simple. What if you had 1,000 of these, huh? What if you had 1,000 Hatsune Miku figures? You'd be in heaven, wouldn't you? Alright. So for our next algorithm design technique, we'll be talking about decrease and conquer. In this, you want to do 3 things. You reduce the problem instance into a smaller instance of itself. And then, you want to find a solution to the small instance of that problem. And then 3, you want to combine those small solutions into the big one. So, it's like you're breaking it down, and then it's feeding back into itself to solve. Ooh, it's a little spaceship. Alright. And then, next after that, oh god, go away. After that, you can do this approach in one of 2 ways. You can do a top-down approach, which is recursive, or it lends itself to recursion, I should say. Or you can do a bottom-up approach, which lends itself more to an iterative implementation. So, like loops and stuff. There's 3 different kinds of decreasing a problem. You can decrease by a constant, which typically you're going to reduce it by 1. And you might see that in a topological sort problem. You might see it very soon, who knows. You can decrease by a factor, a constant factor, which is usually 1/2, and you might see that in a binary search algorithm. Or there could be a variable size decrease, so like it changes the size you're reducing it each time. I'll put a question mark. And you might see that in a partition based algorithm. Those ones are the weird ones for sure. But yeah, let's talk about our first example, the topological sort. Told you you'd be seeing it soon. It is not bad at all. If I can get my pencil to work. Cool. Alright, so for a topological sort, what does that mean? Well, you're basically ordering a graph. It requires the graph. Let's say we have that, and that. Now, a key thing is it needs to be a DAG, and that is not an anime protagonist or whatever. It is a directed, acyclic graph. Now, acyclic, that means no cycles. Directed, that means like arrows, like it can't go both ways in between the vertices. It needs to go one way. So let's draw that. Cool, perfect. So now it's that, and there's no like circles. Like if I follow all these paths, it leads somewhere. It doesn't go in a circle. And then we can label these as, I don't know, 1, 2, 3, 4, 5. Alright, so our algorithm will be, I think it's depth first search approach, which basically means if there is, what was it? I think it was no incoming, no outgoing. No incoming, I was right. No incoming edge. We want to delete that vertice and the edge coming from that vertice and place it in a stack data structure. So if this is going to be our example, we want to take the ones that have no incoming. So that one has one coming in. That one has one coming in. This one has 2 coming in. These 2, none coming in. Which one do I do? It doesn't matter. Whichever one you want to do. It doesn't matter. I'll start with C1. So we're deleting C1. We're putting it in this bucket we're calling the stack. So C1. So now that one's gone. There's no edge going into it. So now we have 2 with no edge coming in, but 3 does have the edge coming in from 2.
So now we'll delete 2. 2 is next, C2. So now that one's gone and the edge is gone, meaning 3 has no incoming edges still. 4 has an incoming edge from 3, but 3 has no incoming edges because we deleted these and put them in the stack. So now we're going to get rid of C3. And now 4. Now since we just did C3 in there, that means the edge going into 4 is gone, which means C4 has no incoming edge, which means we can put it in the bucket or the stack, or you know what I'm saying. And that just leaves 5 with no one around at all. So C5 is at the top. So now, to get the topological sort, which I don't even think I said what that was, which means a topological sort is where the vertices of the graph, that was the graph that I just showed you, and the 1, 2, 3, 4, 5, those were each vertices. They can be linearly ordered such that the starting vertex is listed before ending vertex. Hopefully that makes what I just did clear. So now that it's all in the stack, we can pop it off. Pop off queen. I'm never saying that again. I am so sorry. So now popping off, we get C5. Then we pop off the next one, C4. And then we pop off the next one, C3. Then we pop off the next one, C2. And then we pop off the next one, C1. So then that gives us our ordered list. Look at that. Because we were placing it down. So now we have a C1, C2, C3, C4, and C5. But wait, John, if that's that, what's going on over here? If I could do either of these, how is this sorted? If I can switch these around, guess what? Topological sorts can have multiple correct solutions. Isn't that neat? So yeah, that's our final answer, and we did it by decreasing the problem one by one, and then assembling a solution from the solutions of the smaller problems. So there you go.
Okay, now we'll look at a divide and conquer algorithm design technique. This is pretty similar to the decrease and conquer, only now instead of decreasing by like subtracting a certain amount, you're dividing. And that looks like a problem of size n. I can't write. Becomes a problem size n over 2. And, 2 of them. And then we solve it. Very similar to the decrease. And then we bring those solutions together for a full solution. Yeah. It's usually done recursively because, it's really good for that. But there's a nice little thing when you use the recursive approach to it. It's called a master theorem, where once you obtain a recursive relation, it should be of this form if you're using a divide and conquer technique. So plus f of n, where f of n, this is a bad background, belongs to some O of n to the d. So you have 3 variables, d, I don't think you can see it, b, and a. So we have a master theorem that states basically, if a is less than b to the d, your algorithm efficiency is going to be, it's going to be big O of n to the d. And then if your a is equal to the b to the d, your algorithm efficiency will equal big O of n to the d log, I believe it's n, yes. And then if a is greater than b to the d, you'll get a big O of n to the log base b a. So yeah, that's a nice little master theorem for when you get a recurrence relation. You can use it and you don't have to do all that math that none of us Well, I like doing, but you probably don't. And then that's the master theorem. To give you a good example of this algorithm design, we'll talk about merge sort, which is pretty good. So given this array, 8, 3, 2, 9, 7, 1, 5, 4, these are all different values, just so you know. Sort it. So we'll do that by dividing it into 2 equal halves, which will bring us 8, 3, 2, and 9, and 7, 1, 5, and 4. And then do it again. We'll have 8, 3, 2, 9, 7, 1, 5, 4 again. And hey, how about we do it one more time for good measure? We'll get individually 8, 3, 2, 9, 7, 1, 5, 4. So now you can compare these two, place them in the right order. So that's 3, 8, 2, 9, still cool, 1, 7, and 4, 5. Starting to make sense, I bet. And then same thing, only we'll do it with 4 elements now, and we'll have 2, 3, 8, 9. And we'll do the same thing over here for 1, 4, 5, and 7. Then we'll combine these two for a nice little finish. 1, 2, 3, 4, 5, 7, 8, 9. Never had a 6, did I have a 6? No. So yeah, that's a good way of demonstrating it, right? You're dividing it by the 1/2, and then you're bringing it back together when you're solving those smaller instances of the problem. And yeah, that's the divide and conquer technique. Alright, and that brings us to the transform and conquer style of algorithm. That's usually done in a 2-stage procedure wherein we transform the problem into something that's more than meets the eye, and then we try to solve it. Now that transformation can take a few different forms. We can simplify the problem, say sorting a list in order to do stuff with it. We can change the representation of the problem to make it easier. Or we can modify the problem into a totally different kind of problem for which there's already an algorithm that we can tap into that's better. So yeah. For this one, we'll be doing the last one, the different problem, basically, by transforming a simple unsorted list into a heap. And a heap is not as scary as it sounds. It is basically a complete, or mostly complete, binary tree where the rule is that every node is greater than its child. So yeah, and there's not necessarily a relationship between the siblings like you might see in a binary search tree. So for example, we can have a heap of 9, 5, 3, 1, and 4, and then a 2. So it's mostly complete, right? And we can see that every node is greater than its children, right? So this heap can be presented in the form of a list that will look something like this.
and we want to keep the index starting at 0 for what we're going to do. Or starting at 1, I mean. Not 0, that's the weird thing. So every left child in a heap that's presented as a list is equal to 2 times the index. So 9's left child would be 5. And then the right child is always equal to 2 times the index plus 1. So then the right child for 9 would be 3, just like over here. And there's some other cool properties, like the parent of any node I is going to be equal to the I divided by 2 and the floor of that. So let's see, the parent of, let's say 4, 1, is going to be 2, 5. And hey, look at that. It's true. And then we can say that all the parents exist in the first half of the list, or n over 2 floor. So it's all in the first half of the list, all the parents. So yeah, that's the property of a heap. Now we're going to use that to transform our list into something that's a heap. Or no, we're going to take an unsorted list, make it into a heap, and sort it using the heap's special properties. If I could get the eraser. Alright, cool. So for our example, we are going to be using our transform and conquer to do a heap sort on the list 2, 9, 7, 6, 5, and 8. Is that right? Yeah. So as you can see, it's not currently in heap form. Right now it looks something like this when we apply our heap array rules to this. It's represented as this. And let's see. So yeah, as you can see, it's not following the rules yet. We need to swap that, and then when it's there, we're going to swap it with that because 6 is greater than 2, and yeah, so 2 will go all the way to the bottom. And then 8 and 7 will need to swap, and then since 8 is less than 9, we're good there to stop there. So after we fix it into a heap, we'll end up with something that looks like this. Perfect. Now, to represent this in array form, we'll be getting it to look like, kind of running out of room, but I'll make it work. 2, 5. Hopefully that makes sense. Yeah, that makes sense. So then, for the process of a heap sort, we'll want to do 1. Switch the root with the rightmost position in the heap. And then we'll want to do the process of heapify, so basically fix it so that it's a heap again. And then, what is it? This is all done on the unsorted section of the heap. And then we just repeat. So let's get some room going here. I'll just rewrite it. It's no big deal. Probably should have done that to begin with. Alright. So what was our, oh goodness. Okay. Okay, so our heaped version of the unsorted list that we started with in the problem was this. So now following this process, these two will swap. So we'll get 7, 6, 8, 2, 5. 9 has now been sorted. We don't look at 9. But now we don't have the heap structure. So what are the children here? 6, and it's 8. So 8 is greater than 7. So swap 8, 6, 7, 2, 5, and the 9's fine. And now we look at the 7 again. Greater, yep, we're good. Yep, we're good. Alright, so now we can, so that was the heapify process we just did. Now we can repeat. So now we swap these two, 5, 6, 7, 2, and now 8 is sorted along with 9. Yeah, we're just doing this again. So 5 is, 7 is the greatest out of its children. So we'll replace that. Yeah, we're good. And then we can do the process again. So now we'll have, whoops, this is 2, 6, and 5, and then 7, 8, 9 is sorted. Now we can do it again. So 6 is the greatest of the children that are left. And we're already sorted. Running out of room, okay. Swap. We'll end up with 2, 5, 6, 7, 8, and 9. Perfect. And then we sort the last little bit by swapping to get that heap order. Which might seem a little redundant because, you know, we're just going to swap them again, but it's the process, right? So that's swap, because now we're in the heap form, and then we'll end up with 2, 5, 6, 7, 8, and 9. And now the list is sorted. And we sorted it by doing a transform and conquer. We made it into a heap. And then we did a heap algorithm to sort it. Pretty neat. Alright, now we're on to our last, or not last. I'm gaslighting you. Now our next algorithmic design.
Alright, that has been
technique,
KAWAII
which is
algorithm
dynamic
analysis.
programming.
Very SUGOi, very
So
wow.
in dynamic programming, the
I
goal
hope you
is
learned
solving
something.
a problem with
Hope you never call
recursion.
an algorithm boring. If you made it to the end,
by
I am using
totally
recursion
shocked.
on
Well done.
very SUGOi of you.
Overlapping
Thank you. Leave a comment if I got anything
to
disastrously
build
wrong.
towards a full solution.
And have a beautiful day.
So
Thank
the
you.
process here is going to be a few steps. 1, you want to set up a recursion equation, and that'll work towards a larger solution. You want to solve the smaller instances. And then 3 is you want to record those solutions to the smaller sub-instances. And then 4, you finally get the full solution from the record of sub-solutions. So this whole process is following a principle of optimality, I think is how you say it. I don't know. I learned it by reading it. And it is, this principle is that an optimal solution is made up of optimal sub-solutions. So basically, the full problem broken down into small problems. If this one is optimal, these are optimal. It's optimal all the way down. Turtles all the way down, all that. So yeah, the most famous example is the Fibonacci sequence right there. But we'll do an actual example to get a good picture of what's going on. Come on. Cool. Alright, so the Fibonacci sequence, the most famous example that everyone and their grandmother has probably heard of, starts with the recurrence equation,
such that f of n is equal to f of n minus 1 plus f of n minus 2. So the previous plus the second previous. Our base cases are f of 0 is equal to 0, and f of 1 is equal to 1. So the tree that you can use to imagine this problem would look something like this, where f of n is equal to f of n minus 1 plus f of n minus 2. Then that can be broken down again into f of n minus 2 plus f of n minus 3. And this one can be broken down into f of n minus 3 plus f of n minus 4. And it goes on forever, however long you want to do it. Alright, so with this in mind, let's use an example for when n is equal to 5. So 5 f of 5 is equal to f of 4 plus f of 3, which is equal to f of 3 plus f of 2, which is equal to, what is it, f of 2, f of 1, and then that breaks down into f of 2 plus f of 1. f of 2 becomes f of 1 plus f of 0. Ooh, we're running into our base cases. That's good. f of 2 becomes f of 1 plus f of 0. f of 1 becomes, oh, that's already a solution. We're good. That, and then 2, same thing. f of 1 plus f of 0. f of 1, we're good. Alright. So now we have all our base cases here. We can solve the first row. So f of 1 equal to 1 because of our base case up here. f of 0 is 0, so 1 plus 0, 1. So that becomes our solution for f of 2. This becomes 1. f of 1, the answer is 1. So now 1 plus 1 is 2, and that's the answer to 3, f of 3. And then we can work down here. f of 1 is 1, f of 0 is 0, so f of 2 is 1, 2 plus 1 is 3 for f of 4, and then that's that whole side done. Now we can go down here. f of 1 is 1, f of 0 is 0, 1 plus 1 is 1, f of 1 is 1, 1 plus 1 is 2, and then, so now 3 plus 2 for f of 5 is 5. So yeah, we say f of, so we said f of 0 was equal to 0, f of 1 was equal to 1, f of 2 we found out was equal to 1, f of 3 we found out was equal to 2, f of 4 was equal to 3, and then f of 5 was equal to 5. Yep, that makes sense. So the Fibonacci sequence for when n is 5 is equal to 5, and you can do that forever. That pattern repeats through nature and stuff. I think flowers follow it sometimes, and like the spiral of galaxies follows it sometimes. So it's a cool thing. It's a really cool thing. And that's dynamic programming for you. Okay, our next concept is going to be space for time trade-offs in algorithm designs. Now these are a very important part of algorithm design. And the main idea is that space and time are inversely related in terms of algorithm efficiency. So if you use more space, you'll use less time. And at the same time, if you use more time, you'll use less space. Fun little fact though, that second part actually wasn't, like, everyone knew that was true probably, but it wasn't mathematically proven until this year, weirdly enough. Or maybe it was last year, but either way.
I mean, that's more about how hard math proofs are in general. But yeah, that was just recently proven, so. I mean, we knew it, but it was proven, so. Pretty cool. Anyway, there's two versions of how this is kind of done. We have pre-processing, wherein we store info about input, and we use that info to solve the problem. And in the other version, it's called pre-structuring, where we use the pre-processed input to make accessing elements of the thing way easier, the input. Like, so this one's about access, this one's about input info. So yeah, this is what made like that dynamic programming thing valuable, the thing we just did. And we probably should have done that after this, but who cares? This is more SUGOi and KAWAII. Anyway, let us work on a problem that deals with all this. So, come on. There we go. So, our example that we're going to use is called a counting sort, where we take an input and we count the total less than of each element in the list. And then the number of elements that are smaller than whatever element we're like comparing with, that number of lesser elements will equal the index of where that element should be placed in the final solution. So take example 62, 31, 84, 96, 19. You cannot see that. Okay. 62. 31. 84. 96. 19. And 47. Okay. So, at the very start, we don't really have anything. But at the first one, we look at 62. Okay. So how many are less than 62? We have 1. We have one that's greater, and since we know 62 is less than, we can put that one in the 84 column, because we know 1 is going to be less than 84, and that's the 62. So 62, same with 96. It's going to have 1 less, the 62. 19 is less than 62, so 62 is going to have an extra one in the less column. And 47 is also less. So these are recorded as zeros if they're less than. So then 62 ends up at 3. Perfect. So now we're done with that one. We look at 31. 31 is going to be less than that one, so we add that. We don't add to that column. 96, we add to that. 19 is less than 31. 47 is not, so we add to the 47 column. So then 31 is going to come up as, I don't even know what I was thinking, 1. It's going to come up as a 1. And 84, now we can look at 84. 96, it's greater, so we add another 1 to that column. 19, it's less than, we add it to that column. 47, it's less than, we add it to that column. Total here, we're going to get is 4. Now we move on to 96. Less than. So it's going to get 2. And we end up with 5. Then 19, it was zeros all the way down, so 19 is going to stay at 0. And 47 is also less, so that stays 0. But 47 does get a 1 from the 19. And 47 doesn't have anything to check anymore, so that one ends up as 2. Alright, so now each of these numbers here represent the index position of the corresponding values up here. So with this in mind, we know the first element, the 0 element, is 19. We know the second element is going to be 31. We know the third element is going to be 47. We know the fourth element
is 62. Let me know the fifth element. I'm losing track. Is 84. And the sixth element is 96. And yeah, like that, it's all sorted and pretty. So yeah, that's a good example of how you can use space to basically do your work for you. Alright, that has been KAWAII algorithm analysis. Very SUGOi, very wow. I hope you learned something. I hope you never call an algorithm boring. If you made it to the end, I am totally shocked. Well done. Very SUGOi of you. Thank you. Leave a comment if I got anything disastrously wrong. And have a beautiful day. Thank you.